This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 3303 solids. We're reviewing exam number 2. We've got 3 problems, or 3 pages from the test. The first one deals with Hooke's law, which is Young's modulus, and Poisson's ratio. We're given an assembly as loaded as shown, 3 tubes or rods connected together with these collars, and they're each 400 millimeters long, loads as shown, 10 kilonewtons, 2 times 8, 2 times 15 in the other direction, and 4 at that end. It's in static equilibrium. You sum those up. The diameters of the outside parts, the pieces we're interested in, are 25 millimeters. And Young's modulus is 2.7 gigapascals. Poisson's ratio is 0.3. So what we have here is we want to know change in length, longitudinal strain, and change in diameter. So change in length is PL over AE. We want to know the change in length between sections C and D. Did I not write D out there? This is point D. Going to need to know that. Okay, so for a 25 millimeter diameter, the area of that cross section, that solid rod, is pi over 425 squared, 490.9 millimeters squared. I need that for PL over AE, which is P. I did a little axial force diagram. Another error, I've labeled it V. It is not shear, it is A, or N, normal force. So, in this section, I just cut a little section down here, just between A and B. Just look at the left half. I have 10 kilonewtons pulling on that end. My internal force is going to be 10 tension, so I've got positive 10. Cut a section here. I've got now 26 kilonewtons pulling to the left, which produces an internal force of 26 kilonewtons. Cut a section here between C and D, and just look at the part to the right. I've got 4 kilonewtons pushing, so I've got 4 kilonewtons of compression in that side, on that side between C and D. That's where I'm interested in. I plotted them all on a axial force diagram here. Anyway, so I've got 4 kilonewtons compression. I want to convert it. I like to get everything into newtons and millimeters, so then I'm working in megapascals. So I've got negative 4 because it's compression. It's going to shorten, times 1,000 to get it into newtons, times 400 millimeters, the length of that section, divided by the area, which is computed up here, divided by Young's modulus, E, 2.7 gigapascals is 2,700 megapascals, or a newton per millimeter squared. Run the numbers. So the shortening is negative 1.21 millimeters. Here I checked my units. They all work out right. Units are our friends and help us check our numbers. Question number 6 was, what's the longitudinal strain in that section CD? And we know from our formula sheet and from what we've learned that strain is change in length, delta, divided by original length. That's easy. I've got a number up here. Negative 1.21 divided by its original length of 400 means it's going to shorten negative by an amount, or the strain is going to be negative 0.00302. It's dimensionless, but I wrote millimeters per millimeter to remind you of that. Number 7, the change in diameter, the lateral elongation or change in length between C and D. I'm starting off with a 25 millimeter diameter. It's going to shorten, so it's going to get wider. So I'm looking for a positive number. I know from my formula sheet that Poisson's ratio, which is given as 0.3, is negative lateral strain divided by longitudinal strain. Well, up here I just figured the longitudinal strain, and I'm given Poisson's ratio, so I can rearrange that. Get my lateral strain is negative negative Poisson's ratio times longitudinal strain, which is negative 0.3, times negative 0.00302. So my lateral strain is 0.00905. And now I plug that into this relationship of lateral strain is change in lateral dimension divided by original dimension. Well, that's my diameter. So rearranging that equation, I get that the lateral change in dimension is positive 0.000905 times 25, my original diameter, or plus 0.0226 millimeters. It does in fact get wider or fatter when I compress it, when I shorten it. Okay, problems 8 and 9 had to do with torsion, shear stress, and angle of twist. I was given a weird assembly, a solid rod from C to B, 70 millimeters diameter, 1.2 meters long, and a tube welded on, I guess, to the end of it from B to A. 70 millimeters is the outside diameter, 55 millimeters is the inside diameter. I've applied these two loads. It's fixed at NC, so it doesn't move, it doesn't rotate or anything at C. Here I have a positive, it turns out, 10 kilonewton meter torque applied at point B, and a 3 negative kilonewton meter force torque applied at point A. And so once again I similarly did a little torsion torque diagram, and I cut a section here between B and A. All I've got is that 3 kilonewton meters. Right hand rule tells me that that's negative moment, so I've got negative 3 from there. Then I cut a section here. I've got negative 3, positive 10 produces a positive 7 kilonewton meters in between C and B. So I'm also given that G, the shear modulus, is 80 gigapascals. Got everything I need to know to solve it. Part 8, question 8, find the maximum shear stress, tau max, between B and C. So I'm going to use the formula. Go to my equation sheet. Torsion shear is equal to T torque divided by rho times rho, distance from the center, divided by J, the polar moment of inertia. For that solid section, J is pi over 2, C to the 4th, C, where C is the radius. Got to be careful about that. Pi over 2, 35 to the 4th. It's a large number, 2.357, 10 to the 6 millimeter to the 4th between section BC. Now I know everything I need to know. So the shear stress is equal to 7 kilonewton meters times 1,000 and 1,000 to get it into newtons and millimeters, times the rho, distance from the center, 35 millimeters, divided by J, the polar moment of inertia, is equal to 103.9 newtons per millimeter squared. Check the units. So I report that as 103.9 or 104 megapascals. Question 9 was find the angle of twist, phi, at end A. Well, C doesn't twist, so it's got to be the cumulative angle of twist from C to B and B to A. So I've written that as a summation of TL over JG, which I got from my equation sheet. I already know the J for the section CB. I need to know from AB. For a tube, it's pi over 2 outside diameter to the 4th minus inside diameter. Radius. So 35 is the outside radius. 27.5 is the inside radius of that tube. Run the numbers, I get 1.459, 10 to the 6 millimeters to the 4th. So now I'm going to plug into the formula TL over JG and just sum them up with respect to their signs. I have a positive torque of 7, turns out million Newton millimeters, times the length. I'm going to work everything in millimeters. It's 1,200, 1.2 meters, divided by J, and G. G is 80 gigapascals, so it's 80,000 megapascals. So I've written it there. I've got everything is in newtons and millimeters. That's positive. Then in this section AB, I've got a negative torque, so I have to reflect that with that sign there, 3 million times 1,800 millimeters long. J is this new J I just calculated for the tube. G is still 80,000 megapascals. I've done the little components. I have positive 0.04455 radians minus 0.04627 radians is a net of just a little bit, 0.00172 radians. So it's negative. So this is the direction, using right hand rule, the positive twist, so it's going to twist a little bit away from me. Okay, problems 10 and 11 were a connection problem where I've got these 5 plates joined by a round bolt. The loads are as shown. Once again, it's in equilibrium. I got 2 times 9 at this end and 3 times 6 at this end, 18 kilonewtons on the whole thing. Given that the failure shear stress is 130 megapascals. So part number 10 was find the average shear stress on the 20 millimeter diameter bolt that connects all 5 of those plates. So the total load we've already figured is noted as 18 kilonewtons. The area of the bolt is just pi over 4 times its diameter, 25 squared. It's 490.9 millimeters squared. Then the key thing is I need to count the number of shear planes on that bolt. So I've got, starting at the top, I've got the sandwich between the top plate and the middle and the second plate. That's 1, 2, 3, 4 shear planes. You got to be careful about that. Now I'm ready to figure. I'm to ask for average shear stress, so that's V over A. V is this 18 kilonewtons. I've converted it into newtons, multiplying by 1,000, divided by 4 times that area, which is the total shear plane, 4 times the area of one bolt, comes out with 9.17 megapascals. And finally, number 11, I was asked to find the factor of safety in the bolt. Well, that's easy. From my formula sheet, factor of safety is tau fail over tau allow. 130 divided by 9.17 is 14.2.